Welcome once again to Free Associations from the Boston University School of Public Health, the Public Health and Medical Journal Club podcast for anyone who is as confused by the latest health study as I am by greeting cards. Why do we still have greeting cards? What is the point of greeting cards?
You don't enjoy getting a greeting card?
No, I do not.
Oh,
do you?
Yes.
Really?
And I actually like to browse them in the store. Yeah. I do. I enjoy them. They're still around because of people like me.
You. It's not just that they're around. They're growing. Like we now have them for Arbor Day and, you name the holiday.
Yeah,
okay.
I'm still traditional when it comes to what holidays I would
what's in and what's out for you?
So definitely birthdays, anniversaries. I'm horrible actually at sending holiday cards, so I don't really do that. But yeah, mainly birthday or
Halloween?
The just because ones.
Halloween?
I think those are the best ones.
Those are nice. Those are nice.
Yeah.
What about Halloween?
No.
Okay, so my mom, if you're listening, my mom does Halloween cards. They're actually very sweet, so I don't mean to be totally dismissive. Thank you, Mom. I appreciate those, but I'm not there yet.
Yeah.
Well,
my mom sends them, but they often also, I love you, Mom, but they often arrive late. So we'll get our Valentine's Day cards in March. But it's still, it's still nice. It's still really nice.
Maybe your mom and my mom should get together and talk about sending cards. Anyway, I am Matt Fox from the Departments of Epidemiology and Global Health here at the BU School of Public Health, and I am back in the studio with Jennifer Ryder.
Hi.
From the Department of Epidemiology here at BU School of Public Health. We are back in the godly studio. Nick is at the helm. We are on cruise control at this point. As a reminder, please do go on and give us a rating on your fancy new iPhone or podcast app of your choice, whatever it is, and visit the Population Health Exchange website where you can find all kinds of population healthy website-y things like our upcoming Winter Institute, which I think you'll really like. I definitely knew about and didn't have to have Nick whisper in my ear as to what was coming up on the Population Health Exchange website. So go have a look. So I wanted to read. We got a new, or actually I don't know how new it is because I can't actually tell anymore, but a new rating or a new review on iTunes that says, "This is probably the best epidemiology-focused podcast available. The amazing and amusing segment highlighting bizarre but interesting science lives up to its name. As a bonus, if you're looking for a recommendation for a website that can facilitate lifelong learning, the hosts have you covered," which I think is fantastic.
That is a really nice review.
Yeah. And, I mean, this person clearly thinks we are the best of the epidemiology-themed podcast, of which there are...
It's a high bar.
At least maybe one other. So we're totally up there. No, actually, I really appreciate it. I thought that was a fantastic review. So now on to the show. Today in our first segment, which is our journal club, we are going to take on a study that looked at the impact of a low-dose radiation and the risk of cancer, a study that was done in South Korea. Then in the second part of our podcast, which is our deep dive segment, we'll talk about a study that had been retracted and then republished and what we think that says about the state of science today. And then in our amazing amusing, we'll get into some things that make us laugh out loud, or we will find out exactly who is eating all the cane toads. So let's get into segment one. So segment one, we're looking at an article on the risk of cancer in relation to low-dose radiation. The study was published in JAMA Network Open. Do I have that right? Because, when I started to read the title here, it said the risk of cancer in relation to sugary drink consumption, which made me realize I may not have updated everything from a previous script. So let me just make sure I got that right.
You are correct. It is JAMA Network Open.
JAMA Network Open. And the study was entitled Association of Exposure to Diagnostic Low-Dose Ionizing Radiation with Risk of Cancer Among Youths in South Korea by first author Jae Young Hong of the Division of Spinal Surgery, Korea University, South Korea. And I thought it was interesting that it came from the Division of Spinal Surgery, but maybe there's a reason for that I don't totally understand, and you're going to explain to me.
Probably not.
I figured. So there wasn't a ton of headlines from this one. This was one that you, Jen, wanted to take on, but I'll read you the couple that I did find from Medical Health News. Says radiology risks ... and other stories. So that's really not much of a headline, is it?
It's lazy.
And then Health Imaging says radiation from imaging exams tied to increased cancer risk. Now, I also would like to say, in the interest of full disclosure, that I read this study right after a trip to South Africa in which I watched the entire HBO Chernobyl miniseries, which freaked me out to no end.
Fantastic series, though, right?
It was amazing. Yeah. I loved it. It has nothing to do with this whatsoever because we were talking about two completely different things, and yet I cannot say it didn't color my reading of this at all. It may have freaked me out. So I just want to throw that out there just so everyone knows the context.
Okay, we'll keep that in mind.
Put that down on my disclosure form.
Yep.
Eats 3 servings of red meat a week and
watched
Chernobyl. Okay, before we get started, what is low-dose radiation?
So low-dose radiation is the type of radiation that you would get from certain medical diagnostic tests, including computed tomography, which is the greatest source of exposure in this particular study.
Okay. Would it include X-rays?
So they do look at certain X-rays in the study as well. Yes.
Okay. So probably those would be two of the main sources. I don't know. And the reason I'm asking you this is because I tried to look it up. What constitute, not from the study, I mean just in general, what would constitute low-dose radiation? I didn't find much, but what I did find on Wikipedia was that when asking about low-dose radiation, it said, for example, at one time, assistants in shoe shops used X-rays to check a child's shoe size.
I had heard about that. Yes.
Really?
Yeah. Isn't that amazing?
This is like totally bizarre. I mean,
I imagine
sense,
it's
right?
probably very accurate. Yeah. And sometimes it is hard to know, like where your kids' toes end up in the end of that boot, that winter boot.
We've got this amazing new technology. We can see through and not knowing that this was going to cause all kinds of problems. But I thought that was kind of fascinating. Okay, so enough of me telling you about my fears of Chernobyl. By the way, I got to say that Chernobyl thing was I am so glad that in 1986 I did not know what I know now about Chernobyl because I would not have slept for years. Anyway, back to... So
can I, little aside of that, after watching the show myself, I recently met someone through professional circles who is a childhood survivor of Chernobyl.
Wow.
Yeah.
Wow.
And is actually also a cancer survivor, but immigrated to the U.S. To receive cancer treatment.
Amazing.
Because it still wasn't being acknowledged there.
Unbelievable. I do actually highly recommend that people go and see it because it is really an incredibly well done and mostly accurate from listening to the podcast series that came after it, that most of it was actually based on, the actual people who were there and isn't just composites that they put together.
Well, this person actually had watched the show, thought the show was very well done, and had watched with his father, who of course had really lived through this experience as an adult. And apparently it was very emotional, as you would expect.
Okay, while we're on this tangent, I just have to say, if you listen to the podcast series about this, so it was with the guy who made the series, and Peter Sagal from Wait, Don't Tell Me was the host, and they go through it, and he was talking about how they had lots of consultants on to try and make sure it looked incredibly accurate and realistic. I was a Peace Corps volunteer in Turkmenistan, so former Soviet Union, so I have a very good sense for what the Soviet Union looked like in the 1980s. I was there in the 90s. And one of the things that they said was, so they had there's an opening scene. In the opening scene, they show the, spoiler, but they show the scientist committing suicide. And before he does that, he feeds his cats. And they were saying in the original draft, they pour the cat some cat food. And the consultant said, no. In the former Soviet Union, there was no cat food. You just gave your cat what you didn't want to eat. And I will tell you that, so many of the things that are in there that are incredibly accurate to life in the former Soviet Union in those days. That is not what we're here to talk about. Sorry for that tangent. Nick will decide later whether or not all that gets to stay in. But anyway, low-dose radiation and risk of cancer. Can you tell us what this study was all about?
Sure. So there was another study published in JAMA in 2019 showing that the use of CT among children has either stabilized or declined in both the US and Canada over the last several years. But nonetheless, the use of low-dose ionizing radiation is very widespread. And so there have been longstanding concerns about cancer risk resulting from medical-related exposure to low-dose radiation. There is a prior study mentioned by the authors of a very large study, 180,000 young people who were exposed to CT scans in the UK, which found an increased risk of both leukemia and brain cancer that increased with increasing radiation dose. But the authors note that few studies have really focused specifically on low-dose radiation among young people, and so that was the goal of their analysis. So to do that, they included over 12 million individuals, about equally split between boys and girls, who were enrolled in the South Korean National Health Insurance System claims database. So that database includes nearly 50 million nationally representative individuals in South Korea. And this health insurance system actually started a special support program for individuals with rare and intractable disease, of which cancer is included, since 2006, which basically means that 90% of medical payments for patients with a confirmed cancer diagnosis would actually be included in this database. So it does seem like they have good coverage of the different procedures.
Yep.
They included children and young adults aged 0 to 19 years at baseline. They excluded all individuals with a prior cancer diagnosis, and they followed the individuals included from 2006 through 2015. The exposure was any diagnostic low-dose radiation exposure. As we'll talk about, that's primarily in the study from CT scans. They classified exposure as ever versus never, but also did additional analyses that looked at the number of exposures, so the number of scans that a person had had. The outcomes of interest were overall cancer risk, as well as solid tumors overall and by specific type. And then they separately looked at lymphoid and hematopoietic tumors overall and by type. For the analysis, and maybe we'll talk about this a bit more, I felt like they were a little sparse on details.
I'm with you on
in
that
the
one.
Analysis. Yeah.
I'm definitely with you.
But what I do understand is that they use Poisson regression to estimate incidence rate ratios for cancer, comparing exposed to unexposed individuals, adjusting for age and sex. Keep in mind, this is a claims database. They did lagged analysis, and that was done so that scans that were related to a diagnostic workup could not be associated with risk of developing cancer.
Can you explain what that means, lagged analysis?
Yeah, so basically they looked at a few different lag times, 1, 2, and 5 years. For most of their analyses, they ended up using the 2-year lag period, which basically just means that any, say, CT scan that happened within the 2 years prior to cancer diagnosis couldn't count. So that's what it means to lag the analysis by 2 years.
And I think we're going to spend some time talking about that because I think that's
It's a key.
It's key, and yet I don't know what to do with it totally. But
Yep.
Go ahead.
They, in addition to those incidence rate ratios, they also reported the number of excess cancers in the exposed group. And they used something that I had to look up because I had never heard of it before. And I'm just going to freely admit that, floating confidence intervals.
It's on my last word list of what is a floating confidence interval.
I'm still not quite sure I know.
I'm pretty sure it's a confidence interval that you get when you're in a beach chair by the ocean, you know.
That sounds nice.
It's a floating confidence
with
interval.
With an umbrella drink
An
of some
umbrella
kind.
drink.
Yeah.
Yep.
Okay.
Yep.
Okay, so in terms of the results of the study, they found that 10.6% of the individuals had been exposed to some form of low-dose radiation.
Does that seem like a lot, or is that because this is a claims database and therefore you're only... I
agree. I mean, we're talking about kids from birth to 19. So yeah, I mean, that does seem, having more than 10% of the individuals have one of these types of scans
seems
by
high to
19
me.
does seem a bit high. And maybe there are reasons for that. 14% of those who were exposed to any form of low-dose radiation actually had undergone more than one scan. Again, the vast majority of exposure was from CT scans, 92%, and primarily those scans were done either to the brain or head or to the abdomen. In the cohort in total, there were 21,912 cancers diagnosed. So the overall incidence rate ratio for ever versus never exposure was 1.64 with a 95% confidence interval of 1.56 to 1.73. For individuals exposed to CT scans specifically, which again is the majority of the exposure, the overall incidence rate ratio for ever exposure was 1.54. And they reported that among the exposed group, which included 987 solid tumors, there were 405 excess tumors. Of those people in the exposed group, there were 457 lymphoid cancers and 159 excess cancers. They also did these analyses where they looked at the type of, or the area of the body that received the radiation versus the type of cancer that was diagnosed. So I won't go through all of these, but just a couple of examples. So compared to those who received any low-dose radiation, those who received radiation to the abdomen had a higher incidence rate ratio for digestive cancers, so 3.1 versus 1.8. For breast, it was 3.4 versus 2.3, and for female genital cancers, it was 2.6 versus 1.8. And, similar findings, as you might expect, were found for chest CTs, so that those who had chest CTs had higher incidence rate ratios for respiratory cancers than for those people exposed to any type of low-dose radiation. And then the solid tumors that they found the highest increase in risk were breast, thyroid, and mouth and pharynx cancers. For the lymph and heme cancers, those with the highest increase in risk were myelodysplasia and other myeloid leukemias. So those are all cancers that affect the blood and bone marrow. And then finally, they looked at the increase in risk that was associated with the number of scans. So they did report these analyses according to the various lag times that they looked at, so 1, 2, and 5 years. For the 2-year lag time, having 3 or more scans compared to no scans was associated with an incidence rate ratio of about 6.
Quite large.
Yes.
Okay, so seems to me the big take-home message is that what they found was about a 60% increase in the rate of cancer, of any cancer associated with low-dose radiation.
Having any type of prior low-dose radiation, yes.
And it seems to me that this is kind of an important study to get right, in the sense that, like with many things, but this one in particular, getting it wrong has consequences, because CT scans, other forms of low-dose radiation, are important for diagnostics, for being able to identify various things that we want to be able to use. And so if we find that there is no risk associated with them when there is, then we're telling people go ahead, it's fine, no big deal, when in fact we're putting them at risk. Whereas if we do the opposite, we tell them there is risk when there isn't, we potentially are underdiagnosing other conditions that we could potentially have an impact on. So this is one, I think is, I don't want to say it's higher stakes than, say, a nutritional study like we've done, but it does feel to me that getting this right has bigger potential consequences in terms of action being taken immediately.
Yeah, and I think that is, that was the reason why I thought it would be interesting to talk about this study. And I do think it's one of the things that the authors are pretty balanced about in their discussion. They note that, overall, a person's lifetime risk of cancer is about 1 in 3. So much larger risk, lifetime risk, than what they're talking about in terms of radiation risk. Mm-hmm. And so it's important to keep that in context.
So you said that about 10% of kids were exposed to radiation by the age of 19.
Yeah.
I found that high, and I wondered, and I don't know the answer to this, whether there's anything cultural to that, whether if you were to look in the United States or in Europe, whether you would find as much exposure, particularly since my understanding is this wouldn't include dental exposures, would it?
Nope. So I don't think dental X-rays are included in
And
this.
I say that's a guess because, of course, this is a health claims database. If they've got dental insurance, then maybe it does. But I don't really know the South Korean medical care system. But I did wonder if you exclude dental in the U.S., I wouldn't think that 10% of kids would be exposed to low dose radiation. But I could be wrong.
Yeah, and I think I'm not exactly sure, but I do think that focusing on that number is important because it leads you to wonder why the kids are getting these scans. And that, brings us right to the biggest potential limitation of the study, which is reverse causation.
Yep, it does.
And, the authors, they do mention that this could be a problem. That is why they do these lagged analyses. But, if a tumor is suspected in a certain area of the body, you're going to get a scan for that. And if nothing shows up on the first scan, you might get another one. And the fact that they have these findings where the area of the body that's irradiated is associated with higher risk of cancers in those areas, I mean, you could say, oh, that's because that area of the body was irradiated, or you already knew there was a tumor there. And that's why you were looking so hard. Yeah.
It's really, really tricky. Now, I want to amend something I said because now that I think about it, I was thinking about CT scans.
Uh-huh.
And I wouldn't expect 10% of kids would have CT scans, but X-rays, maybe. I mean, chest X-ray for pneumonia.
Yeah, but the 92% of the scans done in this cohort were CT scans.
Okay.
Yes. I think
my comment stands. Okay. So then my first question was, what are kids having these scans for? Why are kids having CT scans? I don't know enough to know, but what do people have CT scans for other than diagnosing cancer? Presumably some injuries would require a CT scan, but most of them I think wouldn't.
Yeah, this is where we really miss Chris, right? With his, we miss you, Chris.
Okay. Now, pause right here. Here's the place where Nick is going to edit in Chris saying something later.
Okay.
Hello. This is British Chris Gill speaking. According to the Mayo Clinic website, a CT scan may be used to help diagnose muscle and bone disorders, such as bone tumors and fractures, pinpoint the location of a tumor, infection or blood clot, guide procedures such as surgery, biopsy and radiation therapy, detect and monitor diseases and conditions such as cancer, heart disease, lung nodules and liver masses, monitor the effectiveness of certain treatments, such as cancer treatment, or detect internal injuries and internal bleeding.
Now say, thanks, Chris. That was really helpful.
Yeah, that's really interesting.
Yeah. Nick, if you can't get Chris, just edit yourself in there, okay? All right, excellent. Yeah, I mean, so you and I don't know the answer to this question, but my mind immediately goes to a lot of these have got to be suspicion of cancer.
Definitely. Absolutely.
And so that goes to why they're doing this 2-year lag at a minimum, right? They're essentially saying if the 2-year lag says if a scan occurred within 2 years prior to a cancer diagnosis, then we're going to assume that was a diagnostic and not just an exposure that leads to the cancer. We're going to assume that was part of the diagnostic process, and we're going to remove it, which to me is the right thing to do. And yet I'm somehow left with the suspicion that it's not enough.
Yeah, I completely agree. And they have this very helpful figure in the paper that actually explains lagged analysis, which I think I'm going to use as a teaching tool. It's
Fabulous.
A really great example. But I agree. I think that the fact that 2 years may not be long enough because something could have been suspicious and they didn't see anything on the scan. The scans aren't perfectly sensitive. And so then, there may have been another one. So I agree. 2 years potentially could be too too short of a lag. And in fact, when they do those dose response analyses, they do report the results for 1, 2, and 5-year lag periods. And as you would expect, the results become attenuated as the lag increases. So again, consistent with the idea that there is some reverse causation going on here.
Yeah. And given that we're only talking about a 60, I mean, not that a 60% increase is tiny, but we're not talking about a 3-fold increase or a 6-fold increase, which you are when you got into the dose response. But for the reasons that you say, I think those are problematic. I don't know. I'm not sold on this yet.
And I think, apparently the UK study that was done previously did have information on the indication for the CT scan, which would be really, really important to include here to rule out this whole issue of reverse causation.
And that, I think, is the big thing. Without that, it's hard to have as much faith in these results as I'd like to. I'd like to know. I mean, so presumably breaking a bone is not going to be breaking bones doesn't cause cancer. Although I have seen one study that
claims that it
did claim that. But broken bones don't cause cancer, but broken bones do cause x-rays.
Yes.
And so it would be interesting to see whether this holds in kids who had broken bones. And I started wondering for whether you could ever think of breaking a bone as an instrumental variable in this case. For our listeners, instrumental variables is a kind of analysis that you could do in which you have a variable that is a cause of the exposure has no effect on the outcome except through the exposure and has no common causes of the exposure and the outcome. But I think the answer is no, because I'm guessing there are actually common causes of broken bones and cancers, which would be socioeconomic status related, diet, whatever it is. It probably isn't.
Nutrition, potentially.
I was
first thinking about it, I really like the idea, but I think you're right. Maybe there are
I think it wouldn't
problems.
work. But I do think if you could limit this to just people who had a single, an injury related broken bone, whatever it is that led to the. Probably not a CT. I mean, even in that case, would you have a CT scan? It would lead to an X-ray.
Think so. Yeah, I'm not
but
sure.
I would be more convinced if the relationship there held up, because then I think you're in cases where it's not impossible to me that a broken bone isn't actually diagnostically indicative of cancer. In some cases, bone cancer could lead to broken bones, whatever it is.
Yeah.
But I don't think that's the majority of what would be the reasons why people are getting x-rays for broken bones, and therefore I'd be a lot more convinced if I saw that relationship.
Yeah, I think, again, you need to know why the kids are getting the scan. I also think it's interesting, in the discussion of the paper, I think the authors conflate the concepts of reverse causation and confounding by indication. Did you also pick up on that?
I did. Can you explain the two and what the difference is?
Yeah, so reverse causation, which is, I think, what's really being addressed by the lag period analysis, is, the reason you're getting the scan is actually related to the fact that you already have the disease.
The scan is not causing the cancer. The scan is being done because of the cancer.
Exactly. But confounding by indication is the idea, it relates to the reasons that you're getting the scan. So the idea is that kids who would be getting more scans might also be more likely to or have a higher risk of cancer, for other reasons. So, other illnesses or things that actually could be related to cancer risks. And so physicians would be more inclined to order the scan for them.
And you can sort of see why those get conflated in people's mind. I mean, they do sound like overlapping concepts in the same way that people often conflate selection bias and confounding when you're talking about failure, quote unquote, of randomization in randomized trials. People sometimes call that selection bias, which to me, that's not selection bias, that's confounding, but you could see why people think of it as a selection type thing.
Right.
I think you're in the same ballpark here.
But I think, but it's important to distinguish them, not just because we're picky epidemiologists, but because... Which we are, of course, but because how you would handle that particular bias is very different.
Okay, so last thing I want to get into on this is going back to this issue of the lag, because I have this quirky thing about lags that I get really confused on, because, I very much teach my students to design every when you're designing an observational study, first think of the hypothetical randomized trial that you would do if you could, and then design your observational study to mimic that randomized trial as best you can. And you can't, but at least then know what the compromises you're making lead to in terms of potential bias. If you were doing this as a randomized trial, and you would never do this as a randomized trial, I want to be clear, I'm not arguing for this, but if you were doing this as a randomized trial, you would randomize, kids at certain ages to just get routine CT scans, let's say, X number of them versus getting none of them. And you then follow them forward. And anybody who developed cancer from the time of randomization would be included in your study. You wouldn't exclude, I don't think, you wouldn't exclude ever cases of cancer that occurred post-randomization just because you don't consider it plausible that your exposure yet had an effect, right? So
right, but as long as
does my metaphor just break down here? Or?
Well, no, I think it's fine as long as your study really stuck to protocol. So I think if you really did the scans at planned intervals, that would be fine. The problem only comes into play when, having the disease would affect you to have more scans, right? That's
No. I agree with you completely, but I do think that even in the randomized trial version, we might not consider it plausible. We wouldn't consider it plausible that you have a scan and then the next day you develop cancer and it's causally related.
Right, but doesn't that
but
balance
we still
out?
Include it, yeah, and I think that's probably it, right? It's because we think it balances out.
Yeah, I mean, I think that I guess it depends a little bit on how you classify the exposure. I would have to think about it a little bit more. But but I don't think those scans that happen really proximally to cancer diagnosis would have a strong impact on your...
No, I don't either.
Yeah,
And I don't either. And I think that's why probably it just doesn't make a difference.
No, but I do think... But it's an interesting point. Yeah.
And it is the thing that's always stumped me when it comes to, it also comes up when you talk about induction periods, that we can put induction periods into observational studies.
But you would never do that in a trial.
In a randomized trial.
And
I just struggle with that one. Okay, anything you want to say before I take the last word on this one?
Nope.
Okay, so first of all, I will say you will notice there's a very strong focus on p-values in this paper, which is not a big fan of.
We did a very good job of avoiding them in talking about this, didn't we?
We absolutely did. I think we did a fantastic job. So I have asked this before of the group, but you were not here at the time.
Okay.
This article contains a strengths section at the end. Should articles contain a strength section or just a limitations section? What is your opinion on that?
Oh, so you're saying this study has strengths and limitations, and you're asking if it should just be limitations?
Yeah, I'm not specifically, I'm jumping off of this study, but I'm curious on your opinion about when people include the strengths of their study.
I like the strengths of I like to include the strengths because they may not, given the word limits of the paper, maybe you didn't talk about all of the prior studies that have been done in detail. So some of those strengths above and beyond the current literature may not always be obvious to someone from outside the field. So I like it.
Fair. I'm not a fan, but I hear your points there. Last thing I want to say about this, it's not about this article, although this article does fall into the category, but it is not the author's fault in any way. But I do want to say that sometimes I find that the supplements to articles come across as like a disappointing Christmas present. Like there's this thing there that's going to tell me all the answers that I'm going to get super excited about.
Right.
And then you get to the supplement and it's just a couple of figures that they couldn't include in the main paper, which is totally fine, by the way. I'm not in any way trying to say that there was any incumbency on the authors to make my life joyous by their appendix.
Yeah, but they're underwhelming. I get it. Except for that one lagged figure. I really like that.
No,
that
it's
didn't
a nice
make you
figure.
happy?
It's a nice figure, but it did like give me. I was hoping that we were going to go to the appendix and it was going to have all of the diagnostic reasons, and there was going to be this like extra analysis that was going to uncover everything, and I was going to be all excited. Again, not the author's fault. I have put many articles with no appendix, many articles with appendix that looks just like this. So this is not a criticism of the authors. I just always hoping
you're right. There
all
could
the
have
goodies.
been, and I think we touched on it, but the statistical methods section was incredibly brief. And, if the goal is to be able to replicate the analysis based on the description, that did not happen here. I mean, there are a number of things that, they said they did something with Cox models. I have no idea how those were incorporated. So if it was just a word count limit, yes, that could have all been included in the appendix.
Yep, I agree with you.
So I guess I wasn't going to let you have the last word after all. Sorry.
I'm okay with that. Okay. I'm totally okay with that. I don't need to have the last word. I just need to be the inspiration for the last word. That's all that really matters to me. Okay, so let's move on to segment 2, which is an absolutely fascinating case, I think. So I'm going to try and be succinct on this one, though it's really hard to. So we're going to talk about a study that got retracted and republished. And the reason it got retracted and republished is because it turns out that the authors miscoded their exposure such that they came to the wrong conclusion. And instead of the exposure being beneficial, which is what everybody expected, the exposure was actually harmful. So I'm going to read to you from the JAMA. The study was published in JAMA, published and republished in JAMA. So in the article in JAMA, they say, this is not the author saying it, this is JAMA saying, the accuracy of the scientific record is one of the most important priorities for authors and editors. To reflect this priority, JAMA issues corrections, retractions with replacement, and in this issue, a retraction with republication of an article. On a November 12th, 2018, JAMA published an article entitled The Effect of a Program Combining Transitional Care and Long-Term Self-Management Support on Outcomes of Hospitalized Patients with Chronic Obstructive Pulmonary Disease, a randomized trial, with an accompanying editorial. JAMA was notified by the authors of a major coding error that reversed the results. In other words, you coded your exposure as,
So it was coded as 1 and 2, and then they changed it to 0, 1.
And they forgot the way they coded it. They labeled it wrong. Thus, they came to the exact opposite conclusion. So the authors have provided a detailed explanation of the error. JAMA consulted peer reviewers who agree that the corrected findings were important, and after additional internal review to assess the validity, warranted publication in JAMA. So JAMA essentially says, we looked at their correction. We still think the study is important. We still want to publish it. The reviewers still say publish, so we publish it, but now we're issuing the correction. So then the authors write a letter explaining, so I won't re-say what you just said, which is the explanation for it. And then there was an accompanying editorial that says, science and sound clinical care both rely on honest reporting and, when necessary, self-correction. In this issue of JAMA, the notice of retraction and republication of an article by so-and-so entitled whatever represent a commitment by the authors to ensure an accurate scientific record. Following discovery of an error in the analysis of data from the initial report, the reanalysis by the authors now shows that the study's original conclusions changed remarkably. And that seems to me, they say that a lot, sort of there was this change. I mean, it's an inversion. It's
the opposite of what they initially found.
The results of the study, as in all high-quality research, are important regardless of the outcome. The authors have acknowledged and addressed the error in an open and transparent way. The integrity of science is built on the principle that scientists are forthright in their research, and these authors adopted an earnest approach to amend their error. So what's your reaction to this? I mean, what do you do with this?
I know. So, I mean, as someone who has done a lot of her own statistical programming, I mean, this is my worst nightmare, right?
It's what keeps me up at night.
Absolutely. But at the same time, and the authors go through in their letter, all of the quality control checks that they put into place because this mistake happened. But the fact that it could have happened in the first place in, a high profile trial is a little bit surprising. I mean, the human error of that happening initially is not at all surprising.
Right,
I think it can so easily happen, but just the appropriate internal statistical review wasn't in place is a bit surprising. And, this is something where a reviewer of the paper could not possibly have picked up on this. I mean, it's really, unless you submit all of your data for reanalysis, which of course no one ever does.
Even then, they probably wouldn't have mattered because they would have submitted it coded wrong.
It was coded wrong. Yeah. So it really was entirely up to the study team to figure this out. And I think, the reaction in at least the Twitterverse, I think, was to commend the authors for coming forward with that. And of course, that's true. I mean, it would have been so much worse not to come forward.
And yet it would have been easy to not come forward.
I mean, it's possible that no one would have ever known. I mean, that's
because it fit, and because
it
part of what I think,
hypothesis.
Part of why I think this didn't get detected was because no one said, that seems weird.
Well, and in fact, much of the new...
Because it fit their hypothesis.
Right. And much of the new paper and the rationale for publishing the new version of the paper is the authors had to really jump through hoops to come up with possible mechanisms as to why the intervention could have been detrimental. I mean, it didn't make sense. So in that way, too, the authors found what they expected. And so you think, oh, great, just like we thought. And then it turns out that the truth was much, much more complicated.
Yeah. I do think, I'm one of the people who was on the Twitterverse saying, good for these authors for coming forward. Mistakes do happen. This is, we know because they came forward, but this was very clearly an honest mistake. And this is not the only study that's ever suffered from an honest mistake. And many of them discover it and would never come forward. Right. Because why raise your hand when no one else is raising their hand for you? They could have probably laid low and not gotten away, and probably gotten away with it, because part of the reason I say that is because even if you had fancy, algorithms designed to, like there are people now who are on these crusades to identify fraud, you wouldn't detect fraud here because everything else, all the statistics that go with it are correct. They were just, the sign was wrong.
Right.
It was in the wrong direction. So there's no data fabrication. There was just a miscode. And I'm one of the people who applauds them for coming forward. It is also a great reminder to me that I'm not doing enough to ensure that my work is double checked, and I've this is telling me my worst nightmare could come true, and I've got to do more. What I find interesting, though, is exactly the point that you got to at the end, which is, what does this tell us about confirmation bias, about our when things fit with what we think they're going to show, we don't question them in the same way
as much,
and that when you read the original paper, and I have to admit, I didn't go back and read the original paper thoroughly, the hypothesized mechanisms and the story that you tell about your data, when it fits with what you expect, is, see, that we knew this was going to happen. I'm not saying the authors did this, but I'm saying,
but in order to conduct the trial, they had to believe that.
Yeah,
right?
And so, then you get to let's say they had never. Well, so two things. Let's say they had never made the mistake. Does the first article get published in JAMA in the first place?
That's a great question.
I don't think it would.
Yeah.
I'm not sure because I don't know the field well enough. So I'm not sure. But I think, JAMA patting themselves on the back for saying, well, that's not fair. They didn't pat themselves on the back. But they say we went through the process and we still think it's important in the scientific record, is good for them. But would they have put it into the scientific record in JAMA had it shown, contrary to what they expected? Maybe because it's a trial. I don't know.
I think it's a really good. Sure. It's a really good question because you would have had to, go through all of these complicated. The story. It's not as nice of a story.
It's not as nice a story at all. Okay, so let me give you another example. I don't know if you saw this one on the Twitter sphere either, but this is reported in dailycal.org. I don't know what that is, but this is the story of the UK Biobank. Do you know this one?
I'm not sure.
So an error in the research database UK Biobank resulted in a request for the retraction of a paper from a UC Berkeley professor with implications on past CRISPR research on Friday. The paper, based on the research of Professor Nielsen at UC Berkeley's Integrative Biology Department and postdoctoral fellow Shinzu Wei, asserted that people with the CCR5 delta 32 mutation have a 21% increase in mortality. Originally published in June, the paper was inspired by the work of a Chinese biophysics researcher who have claimed that a similar mutation introduced into twin babies using CRISPR gene editing technology, had this was the story of they did it to prevent HIV infection, but it was highly controversial.
Yeah.
Okay, so they say the authors. I think it's the authors. or Harrison, so I'm not sure who this is because I'm jumping ahead. This is somebody from University of Bristol talking about this. This happens with genetic data. Looking at the genetic code is tricky, but it looks like who was missing the values were not at random. So bias could have been brought in here. In other words, they got data from the UK Biobank, but the UK Biobank was missing some of the information on some people in the study, and the missingness was not at random. So to me, that's a source of selection bias. Is this the same thing?
So what is the ending to that story? Did
so
they
retracted
retract
the paper. So Harrison, so the person who's talking here, was initially skeptical of the paper, conducted the same experiment with different methods, and it did different genetic code and did not find the same association. Nielsen and Harrison communicated via Twitter and email. Nielsen and Wei repeated the experiment with the same steps as Harrison. Their results, however, still showed the mutation resulted in a higher mortality rate. While Harrison's findings did not necessarily refute the paper, he did inspire David Reich, a Harvard University professor of genetics, to replicate the study, which provided enough evidence to nullify statistical support for the original paper. And so the original paper published in Nature Medicine had been peer-reviewed, but the error was not caught prior to publication. Should that study have been retracted or not? I mean, we have studies that suffer from selection bias all the time in observational research that do get published, that eventually get refuted and don't get retracted. So is it the same thing?
So I don't think it's exactly the same thing, because one is an issue of bias and overinterpreting your results based on the limitations of study design or the quality of data you collect or whatever. Our JAMA example on the COPD intervention, I mean, was really a coding error. It wasn't, like you said, it wasn't a problem. It was the inverse of the true finding because it was a coding error. And so, there it's very clear cut that the first paper was wrong. I would say the example you provided was more in the realm of misinterpretation, which is still really important, but I think a different class of mistake.
But it seems like timing matters here because, this is a case where they were able to prove the study wrong fairly quickly. Okay. So, I say that because, there are loads of examples in observational epidemiology where we did study after study after study that all went in the same direction, and then we had a randomized trial come along and prove that they were all wrong. And we don't then go and retract the entire body
because it's the history of trying to answer the research question.
Whereas in this case, they were able to prove the original study wrong almost immediately, and that led to the retraction. I mean, the authors of the original study say, this was an error in data from a public database that we worked on. We should have caught the error, but this is not something you can expect reviewers to do. So we should have. I think that was the authors. I'm not 100% positive. But anyway, Nielsen. So the point being, they acknowledged that their study was wrong, and so they retracted it. But in a lot of cases, we don't know that it's wrong right away, and therefore there's a building body of evidence. So it seems to me there's something about both the timing and the decisiveness with which this was proven wrong that led to the retraction that is different from the other study as well.
Yeah. I mean, I think it also, there's a place for the kind of strength of your conclusions based on the paper as well. Because I think, there are hypothesis generating studies. I know, that term is undesirable in a lot of ways, but sometimes you do the best you can with what you have, and maybe that provides a little information, and you build on that inspires other studies. And, I don't think we should ever get to a point where we start retracting those papers, but we certainly have to acknowledge that there's been scientific progress made, and the way we view those papers may not be the same after better studies are conducted.
Yeah, no, I agree with you completely. I do think there is something, both to the ability to demonstrate the mistake. Quote, I put mistake in quotes there because I don't totally understand whether it was a mistake or a bias that couldn't. I don't know exactly what this is, but there seems to be something fundamentally different about this case. In either case, this is what keeps us up at night and should keep us up at night, that we should be, focused on trying to figure out how to prevent things like this from happening. So anyway, any last words on that one before we move on?
No, I would just say that, we didn't get to talk about a paper for the second segment last time, but I think it relates a bit to this topic. So that segment was going to be about the Wellcome Trust, which funds biomedical research, but also humanities and social science research. So the director of Wellcome Trust has come out and talked about the potential problems with focusing too much on excellence in research and how that might actually have a deleterious effect on research quality. And, I can't remember the exact quote in the article, but it was something about, we only care about the result and not about how we get there or something like that. But I think I think that's also a related point, because if you're in this big rush to publish your findings, and those findings need to be positive in order to kind of raise your status, it puts researchers in a tough position. And I think the idea that some funders are now starting to look at this issue and think a little bit more about what excellence really means is encouraging.
Yeah, I agree with that. I wish we had more time to talk about that. Maybe we'll come back to that on another episode and do that second segment again, because I do think it was an interesting one. All right, well, let's move on to our favorite segment, the amazing and amusing. What do you got for us this time?
So I was standing in line at my local grocery store and noticed a pumpkin spice face mask.
It's that time of year, pumpkin spice.
And really started feeling like it's gone too far.
I want pumpkin spice gasoline additives so that when I drive down the street, my car smells like pumpkin spice.
Yeah. So I was kind of curious where this all came from. So there was an article. It's actually not recent. It was published in Scientific American a couple of years ago, also around this time of year, that talks a little bit about our cultural connection to pumpkin spice, which I thought was really interesting. So, pumpkin spice was originally called pumpkin pie spice, and it wasn't available in its current form as pumpkin pie spice until McCormick put it on the shelves of supermarkets in the 1950s. And then in the 90s is when, it found its way into coffee, and then chaos ensued. But this author of this article talks about how Americans do have a really strong historical connection with pumpkins. And while the colonists weren't baking pumpkin pies like we know them today, pumpkins have an important role in our history. So back at this time of year, hundreds of years ago, people would start trying to preserve foods for the winter. And that meant doing some baking and often using the spices of cinnamon, nutmeg, ginger, and cloves, all which are in pumpkin pie spice or pumpkin spice.
Getting hungry.
And, the other thing about the pumpkin is that it's kind of a reject in lots of other, I don't know what other way to put it, in other parts of the world.
Nobody eats a lot of, people don't eat a lot of pumpkin.
When you travel around, there are a couple exceptions, but especially in Europe, you can't find a pumpkin. They think it's very bizarre, the whole idea that you would eat a pumpkin or a butternut squash. It's just not a flavor that's accepted there. And in fact, back when the immigrants, when there was an influx of immigrants in the U.S. in the mid 1600s, trade really picked up, and the colonies began doing a lot of exporting. But they could get rid of a lot of things, but not pumpkins.
Nobody wanted the pumpkin.
No one wanted the pumpkins. And in fact, Europeans would kind of disparage the colonists and say that they had pumpkin blasted brains for leaving England yes. And pumpkin eating was considered backwards behavior. So the author of this Scientific American article says, the narrative of the pumpkin as a poor man's dinner option moved people away from everyday consumption, but the narrative of the pumpkin as a symbol of American perseverance and agrarian success means that we don't want to forget the fruit.
Oh, yeah.
So she claims that pumpkin spice lets us maintain this nostalgia without committing to the fruit.
Oh, that's smart, because I don't actually want to eat the pumpkin.
Yeah, you just want the spice.
I like that.
Yeah.
That's very cool. Okay, well, are you a pumpkin spice latte person?
I do not do the PSL as it's called, but I do like other forms of pumpkin. But I do feel a bit overloaded. Like I used to love it, and now it's just it's too much.
Yeah.
It's too much.
I've never been
really?
a pumpkin spice.
Pumpkin bread.
No, I love pumpkin bread.
Oh, yeah.
No, I'm just saying pumpkin spice in my coffee.
Yeah, me neither.
Never gone there.
No.
Okay, well, for mine, I have a figure from an article that I would like to submit to the Amazing and Amusing Public Record.
Okay.
So I like when scientists have a sense of humor and try to sneak things into articles without the majority of people noticing.
Like in the acknowledgements?
Like in the acknowledgements. This one wasn't snuck in the acknowledgements. It was snuck in the actual figure itself. So this was an article. I don't totally know what the article was about, but because I can't actually, it was in the Journal of Physical Chemistry B, which, I only read A and C. So I missed this one. But the authors were presenting a figure of various different methodologic approaches on the y-axis, and on the x-axis, they presented the root mean squared error for these different approaches. Now, if you were setting up a figure the way kind of you would normally set things up with the method along the x-axis, and you wanted to put a point and a confidence interval around that, you could put a dot and then the confidence interval coming out
the bar,
the up and down from the point. Mm-hmm. But because they set this up with the method on the y-axis, you now have the point and then the confidence interval bars coming out left and right.
Right.
So they then have their different methods, and each one has a point and a confidence interval with two, bars coming out of the side. If you then go down to the figure title, it says, this figure uses a squadron of Imperial TIE fighters to depict the root mean square error for the 17 initial methods in our ensemble design process, because that is what they look like. So if you remember from Star Wars, the TIE fighters were the Imperial fighters that were just basically like a circle with the two wings that came off the side, and they look like a dot with confidence interval bars coming off the side.
No, and it looks like, to me, like a video. It's the image from like a video game in the early 1980s.
Exactly. Yes. And I think that was just clever.
That is really clever.
And I wish I had the guts to do something like that. So that is the end of our program. If you've got any feedback on this or any other episode, or you want to suggest a study or a topic for a take on, you can tweet us at PopHealthEX, or you can tweet me at ProfMattFox, or Jen at Jennifer R. Ryder.
That's right.
Or you can find us on the Population Health Exchange website at www.pophealthex.org. Don't forget about our upcoming winter what, Nick? What is it called? The Winter Institute. So everyone go there. If you are listening to this and you don't register for the Winter Institute, we'll know that you don't listen all the way to the end. We want to thank Leslie Talalian, Director of Lifelong Learning at the BU School of Public Health, for supporting the podcast, and Nick Guler for sound and editing. Thanks for joining us. We hope you enjoyed it, and we hope you will download our next episode.